Hello, AP Chemistry students. We have arrived at Unit 4, and I'm going to continue to change up how I present these to be a little bit more efficient. This time I'm going to split up the sections into parts that have sort of a theme. For this one, we're going to be doing 4.1 through 4.5, and this is going to focus on chemical equations and stoichiometry. So our learning objectives here, we're going to identify evidence of chemical and physical changes in matter. We're going to learn to represent changes in matter with a balanced chemical or net ionic equation for physical changes, for given information about the identity of the reactants and or products, and for ions in a given chemical reaction. We're going to represent a given chemical reaction or physical process with a consistent particulate model. We're going to explain the relationship between the macroscopic characteristics and bond interactions for chemical and physical processes. And then finally, we're going to explain changes in the amount of reactant and product based on the balanced reaction equation for a chemical process. This last one is going to be our big focus on stoichiometry here. So let's talk about some chemical equations. This should definitely be review if you've taken a year 1 chem, but let's just go over it real quick. So chemical equations can be used to show both chemical and physical processes. You can always tell the difference because in a chemical chains, new substances will be formed. And the types of physical processes that you see with equations are usually ones where a substance changes phase. So let's look at here for a chemical example. We have hydrogen gas combining with oxygen gas to make water vapor. We have two substances making a new substance. Whereas for the physical version here, I have water vapor condensing into liquid water. So the water is staying the same, it's just changing its state of matter. But in either case, substances on the left represent a before state, which we call the reactants, and the ones on the right represent the after state, which we call the products. And the coefficients represent the ratio in moles. So this is a 2:1:2 ratio. Two hydrogens combine with one oxygen to make two water vapors. And then our letters in parentheses represent the states of matter. So this one's all gas. Here we have gas turning into a liquid. If it's S, it's solid, and if it's AQ, it is aqueous. So if you're doing an experiment, you can use observations to identify if a chemical reaction is occurring. And chemical reactions are usually associated with the production of heat or light and or fire, formation of bubbles. That usually means a gas is being formed. Formation of a precipitate, that's a solid being formed in the process. And if it's an aqueous solution, you'll end up with a murky solution or solid bits dropping to the bottom. Or a color change. And you got to be careful when we're using these as our main ways of determining whether a chemical reaction is occurring or not, because some of these can be associated with physical change as well, and we need to consider the context. For example, a solution will change hue if you dilute it. If you have a red solution and you add water to it, it's going to turn more pinkish, and that's just because the dye molecules are being spread out, for example, but nothing's actually changing chemically. Mixing a red and blue solution will make a purple one. That's not a chemical change associated with color change because that's just you seeing red and blue at the same time. If you mixed red and blue solutions and it turned green or yellow or something like that, that would definitely be evidence of a chemical reaction. And also bubbles can form as a substance begins to boil and the solution will feel hot. This one might seem kind of obvious, but if your solution is getting hot and there's no outside source of heat contributing to the kinetic energy of the particles, that will be a chemical change for sure. Or if it gets cold, that's also a good example of that. So sometimes it's useful to represent chemical equations as particle diagrams to show the new bonds being formed. I've seen this come up a lot on the AP exam, so it's just good to familiarize yourself with these. So for example, we talked about hydrogen and oxygen combining to make water earlier. So we have two hydrogens combining with one oxygen to make two H2O. We could represent that using different size and color spheres. You can see these represent the two hydrogen molecules combining with this one oxygen molecule, and we end up with two water molecules. And this is sort of a hint for things we're going to talk about later, but this is also good to show that the number of atoms on both sides are the same. So we have these 4 hydrogen atoms and then these 2 oxygen atoms. Particle diagrams are also useful when we're representing physical change, but it's a little bit more complicated than just showing the compounds. With physical change, you want to identify that the cohesive forces are changing, particularly in a phase transformation. For example, when we have water liquid turning into water vapor. We do need to acknowledge that no chemical bonds are being broken. So the covalent bonds between hydrogen and oxygen in the water molecules are being retained. What is being broken is the cohesive forces between adjacent water molecules. So the intermolecular forces in this case, and specifically the hydrogen bonds. You can see here in this diagram, we have our liquid water where we have hydrogen bonds sort of attracting all of them, and then as it goes to the gas phase, those disappear. There's too much kinetic energy, and those hydrogen bonds can no longer form in the gaseous phase. But the water molecules and their covalent bonds are retained. This can be kind of complex when we're talking about dissolution, though, because dissolution is often debated of whether it's chemical or physical, and sometimes people refer to it as being both. But if you were to just look at the chemical equation, it'd be hard to tell that because here we have sodium chloride solid turning into sodium chloride aqueous. This looks like a purely physical process. But if we consider the mechanics of what's happening, we have our sodium chloride lattice, and then these water molecules are coming in and starting to separate them, forming these hydration shells where the negative oxygen part of the water molecule is going to surround the sodium cations, and the positive hydrogen part of the molecule is going to surround the chloride anions. And this technically means that the ionic bonds in the sodium chloride are being broken. However, they can still be reformed quite easily if you just boil the water and remove it. So if we take away the water molecules, it's going to solidify back into this. So it's less that the ionic bonds are being broken, but rather they're just being kind of temporarily separated from each other, and they can easily be reformed if you remove the solvent. So now let's talk about ways we can use chemical equations. So one important thing about chemical equations to first get out of the way is that they need to accurately portray a chemical change, and therefore they must obey the law of conservation of mass. This is one of the most important ideas in chemistry because everything we know about how things combine and the quantitative aspects of chemistry depends on the fact that no matter can be created or destroyed in a chemical reaction. All of the atoms are going to be retained. All of the mass is going to be retained. They're just going to sort of shift around and form new substances. So let's look here. We have nitrogen and hydrogen forming ammonia. So we know the identities of the substances, but if we look at a table of how many atoms there are on each side, we can tell that this is not balanced. So we're going to have to manually balance it by adding coefficients. So let's look here. We have nitrogen. There's 2 on the reactant side, 1 on the product. For hydrogen, there's 2 on the reactant side and 3 on the product. So we're going to want to alter these by adding coefficients. And the important thing to consider here is all we can do is add coefficients. You can't just say that, oh, well, I have 2 hydrogens here, but I need 2 over here. I'm just going to change this 3 to a 2. You can't change the overall formulas of the substances. You can only change the ratio in which they appear in the equation. So in this case, since we have 2 on the reactant side and 1 on the product side for nitrogen, let's add a 2 in front of the ammonia and see where that gets us. So that gets us to 2 and 2. Our nitrogen is now balanced. But since the hydrogen is also attached to ammonia, that also changes from 3 to now 6. But that does give us a jumping off point to then balance the hydrogen as well. Since we have 2 hydrogen, we have these H2 molecules, and we need 6. That means we're going to need 3 of these in order to get 6. So we'll add a 3 to the reactant side in front of the hydrogen. So now we have 1 to 3 to 2 as our ratio, and you can see that ends up giving us a totally balanced equation where we have 2 nitrogens on both sides and 6 hydrogens on both sides. And we can now proclaim that our equation does obey the law of conservation of mass. And this is further proved if we draw a particle diagram, because we'll see that there are 2 nitrogen atoms, which end up 2 on the other side, and then our 6 from our 3 hydrogen molecules end up getting spread evenly between the 2 ammonias. All right. Sometimes chemical equations can be a little bit more difficult to balance, and you need some additional tricks. So let's. This is often the case for reactions that show combustions of hydrocarbons, which are molecules made of carbon and hydrogen, that contain even number of carbons. So let's consider the combustion of ethane, which has the formula C2H6. All combustion reactions are going to involve a hydrocarbon reacting with oxygen to form carbon dioxide and water. So let's set up our table. We have 2 carbons on one side, 1 on the other, 6 hydrogens and 2 and 3 oxygens. This is super unbalanced, so we're going to have to add some coefficients to make this work. One recommendation I have for this type of equation, and basically any kind of chemical equation, if you have an atom that appears in multiple substances, say like this oxygen, for example, it's in both the CO2 and the H2O, I recommend balancing that last, because if you can get the carbon and the hydrogen balanced, then you'll know how many oxygens you need. But if you start with the oxygen, you're going to be fiddling with these and you're going to be constantly changing the carbon and hydrogen, and it's going to be hard to keep everything balanced. So let's start by balancing the carbon. We have 2 on one side, 1 on the other. Let's add a 2 in front of the carbon dioxide. You can see that now we have balanced carbons. That also changes the oxygen to 5. We're not going to worry about that just yet, but we have 2 times 2 there. It's 4 plus 1, 5. Like I said, we're gonna save the oxygen to balance for last. So now let's balance the hydrogen. We have 6 here and 2 there. So if we add a 3 in front of the hydrogen, that should get us a balanced hydrogen situation. So yeah, now we have 6 and 6. So both carbon and hydrogen are now balanced. But you can see here we have a little bit of an issue with the oxygen because we have 2 on the reactant side, but 7 on the product side. And the molecular oxygen comes in pairs. So that means that we can only have an even amount of oxygens. And since we have an odd number on this side, there's no way we can balance it by adding a whole number. So there are 2 possible solutions to this. First is ignore doing a whole number at all. So if we had a 7 halves in front of the O2, that's like 3.5, like 3.5 O2s are technically going to be 7 oxygens. But adding like a 7 halves to the equation is a little bit cumbersome, even though this is technically a correct way to represent this. And that's because it's possible to imagine that you have 7 halves of a mole of oxygen, because that would be a real number of oxygen molecules. However, if we're considering like the particulate way of looking at these, you can't have 7 halves individual molecules, because you can't have half of a molecule. So the other solution here to then also make that make more sense from a molecular standpoint is to multiply the whole equation by 2, because 7 halves times 2 is going to be 7, and that's going to give us a whole number there. So here now we have 2 ethanes because we multiplied it by 2, 7 O2s because 7 halves times 2 is 7. The 2 becomes 4 and the 3 becomes 6. And it doesn't affect the ratio if you multiply everything by the same number, because they're still going to have the same relationship. A 2 to 6 to 7 relationship is the same as a 4 to 12 to 14. So our thing is still going to be balanced, and that does get us the same number of oxygens on both sides. So therefore, we now have a balanced chemical equation with a 2 to 7 to 4 to 6 ratio. Another important thing we can do with chemical equations is turn them into net ionic equations. This particularly is important for doing ionic reactions, particularly double replacement precipitation type ionic equations. And this is used to simplify a reaction to show only the ions that are actually reacting, only the places where the chemistry is actually happening. And we're going to be ignoring ions that are not involved, which we call spectator ions. Those are the ions that are present in the substances that you added, but not taking place in the actual chemistry. So let's look at an example of this. Let's consider the reaction between an aqueous solution of calcium chloride and an aqueous solution of silver nitrate. So we have our CaCl2 aqueous combining with AgNO3 aqueous. It's going to be a 1:2 ratio. That's going to form calcium nitrate aqueous and solid silver chloride. And we're going to form 2 of those. So if we think about what it means to be aqueous, and we think about what we talked about earlier with ions splitting up in water as they become aqueous, these actually are going to split up into their component ions. So calcium chloride is going to split up into calcium and chloride. So we're going to have Ca2 plus and then 2 Cl minus. Please note that it's not going to be Cl2 in the products. This is something that I see students do over and over and over. That is a big pet peeve of mine. This is an ionic compound. This means it's a combination of ions. The ions involved are calcium 2 plus and chlorine 2 minus. The 2 subscript doesn't mean that we have a chlorine molecule. It means that we have 2 chloride ions per every 1 calcium. So make sure that you represent that sort of thing accurately. Our silver nitrate is going to split up into Ag plus and NO3 minus, and our calcium nitrate, our CaNO3 is going to split up into calcium 2 plus and 2 NO3 minus ions. You'll note here that I didn't include the AgCl because this is a solid, and solids are, especially if a solid is being formed in a process, that means it is insoluble. It is going to precipitate out of the solution and become like a hazy looking like solid in the solution that's going to settle to the bottom. The AgCl is not going to split up, but we can use the fact that these other three compounds do split up to rewrite the equation to reflect that. So our equation then becomes this, where we have calcium ions plus chloride ions plus silver ions plus nitrate ions, since these are both aqueous compounds that split up, forming calcium ions plus nitrate ions plus 2 silver chloride solid. We note that we don't split this one up because it is a solid. It is insoluble. It is not going to be aqueous in the solution. So the above equation that we wrote here, this is either called a total ionic equation, a complete ionic equation, or sometimes just an ionic equation. And this is where we show all of the ions involved, all of the ones that split up into their component parts due to being aqueous. And from this, we can see that there are things that aren't involved in the overall change of the chemistry. If something appears on both the left side and the right side of the periodic table on its own and unchanged, that means it's not really part of the chemistry. And let's highlight the things that are doing that. We can see here that calcium 2 plus is still calcium 2 plus on the product side, no change. Our nitrate is still going to be on the product side, no change. The only thing that actually changed here was that the silver ions and the chloride ions came together to form the silver chloride solid. So that's going to be our focus for our net ionic equation, which is just showing us what is happening in this process. So all of these red things, these are our spectator ions. These are the ones that are just in solution, not contributing to the chemistry. We can delete these, and then we'll be left with the equation 2Ag plus 2Cl minus, making 2 AgCl. And this gets us closer to our net ionic equation. However, we're not quite there yet for one simple reason. This equation shows that we have a 2 to 2 to 2 ratio, which is the same thing as a 1 to 1 to 1 ratio. An accurate chemical equation should always show substances with the most simplified ratio possible. So if there's a common divisor that you can incorporate into all of your coefficients, you should always simplify it to be the most simplest form. So we end up with our final net ionic equation of silver ion plus chloride ion, making silver chloride. And it doesn't matter that this is 1 to 1 to 1, when in the original equation it was 2 to 2 to 2. The 2's only mattered when the calcium chloride was present and the calcium nitrate was present in order to make sure that is balanced. What's actually happening at the atomic level is that one silver ion and one chloride ion are coming together to form a formula unit of AgCl. So if you follow this process and discover that nothing changes from left to right, aka everything on the reactant side and the product side are spectator ions, that's actually a sign that nothing is happening in the chemical equation. So sometimes the chemical equation will be technically an illusion. For example, if you had ammonium nitrate and sodium phosphate combining to make ammonium phosphate and sodium nitrate, all four of these compounds are aqueous, which means that all of those ions were just floating around in solution. Nothing is actually combining. And if you were to write a total ionic equation, you would just see basically the same thing on both sides. Nothing new is being formed, and all of the spectator ions would cancel out, and you technically would have no equation or no chemical reaction actually happening. All right, now it is time to talk about stoichiometry. So hopefully you already have a bunch of experience with this. I am going to go over a bunch of examples anyways, but let's look at what stoichiometry means. This is the process of using the measured mass or volumes of substances and using them to quantitatively predict the amount of other substances that are either needed, aka like another reactant or so, or are formed in the reaction. You could also kind of start from the endpoint and say like, oh, I want to form this many grams of a substance. How many reactants am I going to need? You can always relate the different substances in a chemical equation quantitatively through this process. And this is especially important because things like mass and volume, they need to be weighed out in either grams or milliliters or things like that. And that doesn't necessarily reflect the same relationship that things have in the mole unit, which is our main thing that we use to compare them in the actual ratio. So, whoops, I had to cough, so I had to pause the video. All right, getting back into it. So for stoichiometry, the general process for mostly any full stoichiometry problem is first you're going to convert your measured value that's either in volume or mass into moles so that we can directly compare the ratio. And then we're going to determine if one reaction is either limiting or excess, because that's going to control how much product we can make. Because as soon as something runs out in the equation, it's going to stop happening. Even if there's more of one of the reactants left, it's not going to get used if one of the other ones runs out. So once we know that, we can convert our moles of one substance to moles of another, usually using the limiting factor and the mole ratio in the balanced chemical equation. And then finally, we're going to convert our moles to whatever desired unit that we want, either mass or volume, depends on what we're trying to find. And you're not always going to need to do every single step here. You need to kind of be able to figure out where in the process you're starting from based off of the information given. But let's go over some examples. So first off, let's talk about potassium chlorate, which is breaking down into potassium chloride and oxygen in a 2 to 2 to 3 ratio. First off, we should try to define the mole ratio between the different substances, because this is going to be important if we're doing any stoichiometry with it. So potassium chlorate and potassium chloride from the equation are 2 to 2, aka 1 to 1. And then the mole ratio between potassium chlorate and oxygen is going to be 2 to 3. When we're showing that in a as a ratio, it's usually going to be a conversion factor, like in dimensional analysis when we're doing stoichiometry problems. So usually you'd write it like 1 mole of potassium chlorate over 1 mole of potassium chloride, or vice versa, depending on what unit you're starting with and which one you're converting to. And like, 2 to 3 between potassium chlorate and, oh, this should be oxygen. That's a typo. All right. Next, let's see how many grams of each product we can make from 61.3 grams of reactant. So we're starting with 61.3 grams of our potassium chlorate, and we want to know how many grams of each of the reactants we can make. So we're going to need to do those one step at a time. So we start with our 61.3 grams. First, we're going to turn that into moles, this time using the molar mass of potassium chlorate, and we're going to be dividing by it so that the grams cancel out. We have moles on top, and we get units of moles. So it's going to be 0.5 moles of potassium chlorate. And then from here, I can convert this to both of our masses of product. I don't need to consider if there's a limiting reactant or not in this one, since there is only one reactant. So let's start with the ratio of potassium chlorate, potassium chloride. I'll have the potassium chloride on top and the potassium chlorate on bottom. Basically 1 to 1, so multiply by 1, divide by 1. And then here, now I have moles of potassium chloride, and I'm going to convert that directly to grams. The way I like to do this is to save myself some time and not end up rounding too much. I like to put all of the dimensional analysis unit conversions in one line and just calculate it all at once. So in this case, I'm going to do 0.5 times 1 divided by 1, and then multiplied by the molar mass of the potassium chloride, which is 74.55. We end up with a value of 37.3 grams of potassium chloride formed. For the oxygen, we have the same starting point of potassium chlorate. That's going to be 3 over 2 for our mole ratio, and then multiply by the molar mass of oxygen this time. That's going to give us 24.0 grams. And if you're ever doing a problem like this where you know the total mass of reactants and you try to figure out the mass of the products, it should always obey the conservation of mass. So you can check your work by adding the two values from the products together, and we end up with 61.3, which tracks. So now we do have a conservation of mass, which means that we did this correctly. If you have more than one product, though, or sorry, more than one reactant, and you're not given the grams of the other one, you can't really check your work this way unless you go through and actually calculate how many grams of the excess reactant are being used. All right, let's look at another example. So here we have O3, which is ozone, turning into O2, which is molecular oxygen. They have a 2 to 3 ratio. And this problem is going to be slightly different because instead of starting with mass, I want us to either start with milliliters of O3 gas at standard temperature and pressure, and we're going to convert it to milliliters of O2 gas. And in this one, we're going to go from mass to volume. So either volume to volume or mass to volume. So let's look at how we solve this. So for the first one, we start with our 0.0250 liters. I converted my milliliters into liters. And the reason I did that is because we're going to be utilizing the molar volume of an ideal gas at standard temperature and pressure. If you remember from the gas lab, we were talking about how 1 mole of a substance at STP, 1 mole of a gas, is always going to occupy 22.4 liters of space. So we can use this as a conversion factor between moles and volume. So my 0.0250 liters times 1 mole over 22.4 liters, that's going to get us to moles of the ozone. And then I multiply by the 3/2 ratio to get moles of O2. And then lastly here, I'm going to multiply by 22.4 to get it back into volume. This one might seem a little bit redundant because these two conversion factors are actually going to cancel each other out in the end, and you're basically just multiplying by 3/2. But the important part of showing all of this is showing the logic of how one unit turns into the other one. So you still need to show this whole process. So now let's look at the 25 grams of ozone example. We're still at standard temperature and pressure, so we can still use our molar volume of an ideal gas. So we have our 25 grams. This time we're going to have to convert that into moles using the molar mass of ozone. We multiply by the same ratio to get 2 moles of oxygen. And then since we're trying to get to volume of oxygen, we can just multiply by the 22.4 liters per 1 mole again. We end up with 17.5 liters. And I'm now realizing that both of these questions asked for milliliters. So this one would be 37.5 milliliters. And this one, since that's 17.5 liters, that'd be times 1,000. So that'd be 17,500 milliliters. Now, say we're going to do the same chemical equation, but we're no longer at standard temperature and pressure. We're going to have to alter our process a little bit. So we still have our 25 grams of ozone, but this time instead of a pressure of 1 atmosphere and a temperature of 273.15 Kelvin, we're dealing with half of an atmosphere and 200 Kelvin. So we could start the same way. We could still turn our mass into moles using the molar mass, and we could still get to moles of O2 using the mole ratio, which gives us 0.780 moles of O2. Now, since we can't use the molar volume of an ideal gas at STP, we're going to have to use the ideal gas law, which, if you can recall, can relate moles of a substance to its volume, pressure, and temperature. And so since we know the pressure and temperature, we can use it to solve for just the volume. So V is going to be equal to nRT over P. So we're going to multiply the moles we found by the gas constant, and then by the temperature, and then divide it all by the volume. And then we end up with 25.6 liters of oxygen formed. So the volume stuff can also be applied to solution stoichiometry. So say we're given 45 milliliters of a 1.5 molar hydrochloric acid solution. And this is going to be combined with an excess of solid magnesium. So this is the first example where we've had 2 actual reactants. So we need to know which one's limiting and which one is excess. And if in the problem they literally tell you how much you have of one and that you have excess of another, we can assume that the amount of magnesium that is reacting here, or the amount of magnesium that we have, doesn't matter. It's going to be as much as we could possibly need. So the amount of products that are going to be formed are going to be solely based off of the hydrochloric acid in this example. And I hope you all remember this is the same equation that we did in the gas lab. So we are at 25 degrees Celsius and 1 atm, so we're not at STP, so we're also going to have to use the ideal gas equation. And we're trying to solve for 2 things here. First, how many liters of hydrogen gas are going to be formed, and then what the concentration of the magnesium chloride solution that is formed as a result of the equation is going to be. So for part A, first we're going to have to use our volume and our molarity to calculate moles. So if you know the volume and you know the concentration, I converted this to liters because 1.5 molar is in moles per liter. And if I multiply the volume in liters by the molarity, the liters are going to get canceled out, and then we're going to get just the moles. So 0.045 liters times 1.5, that's going to give us 0.06750 moles of hydrochloric acid. And then I can multiply this by the mole ratio, which in this case for hydrogen is going to be 2 to 1. So we have 1 mole of hydrogen over 2 moles of the hydrochloric acid. That gets us to 0.03375 moles of H2. And now we can plug this into the ideal gas equation to turn it into volume. Much like the example before, we saw for volume, moles times the gas constant times the temperature. I converted it into Kelvin from Celsius divided by the pressure. And we end up here with 0.826 liters of hydrogen gas. For part B, we're trying to solve for the concentration of the magnesium chloride solution. So I could start kind of at the same place. I already know that I have 0.0675 moles of hydrochloric acid. I can multiply that by the ratio to magnesium chloride, which is also 1 to 2. So we end up with 0.03375 moles of magnesium chloride. And then to get the concentration, I'm going to need to divide the moles by the volume. Since there was a solid and a liquid, I can use the volume of the liquid because no other liquid is being added. So I can assume that the magnesium chloride solution, when it is formed, is still in 45 milliliters. So I can take that volume, take the moles, divide it by the volume, 0.03375 divided by 0.045 liters, and we end up with 0.750 molar magnesium chloride as the resulting solution concentration. Let's look at this one. So now we have the combustion of ethane. This is the one I showed earlier. We have 2 ethane molecules combining with 7 oxygens to form 4 CO2s and 6 water molecules. And in this case, we have 10 grams of the ethane and excess O2. So much like in the last example, we don't care how much oxygen we have. We have enough. And all of the 10 grams of ethane are going to react in this case. So now we want to know how many grams of each product can we make? And then also, how many grams of the oxygen were used? We know the oxygen is in excess, but if we wanted to, we can actually calculate how many grams of oxygen reacted, even though we don't know it based off of the starting values. So we start pretty similarly to other ones. We take our grams, we convert them into moles. In this example, I've just done all of the dimensional analysis in one go. So for the first example, to calculate the grams of CO2, I divide by the molar mass of ethane, multiply it by the mole ratio of ethane to CO2, and then multiply by the molar mass of CO2. And we end up with 29.3 grams of carbon dioxide. I can do the exact same thing for the water. The first step is going to be exactly the same. I changed the ratio to match. The first one was 2 to 4, aka 1 to 2. The other one is 2 to 6, aka 3 to 1. So it's going to be 3 moles of water over 1 mole of ethane, multiplied by the molar mass of water this time, and we end up with 18.0 grams of water. Now, the last thing we want to do is figure out the grams of oxygen used. And there's 2 ways to do this. First, we can look at the grams of total product formed since we calculated both of them. We had 29.3 grams of CO2 and 18 grams of water. That means that 47.3 grams of product were formed. And that means that if we have conservation of mass, we can actually figure out the mass of oxygen used just by subtracting the mass of the other reactant, which was 10, from the total mass of the system, which was 47.3. So if I subtract 10 from 47.3, that gives me 37.3 grams of oxygen used. So this is a totally fine way to do this if you have this much information about the masses of the reactants and the products, as long as you show all of your logic and reasoning like I did here. However, if I wanted to do it stoichiometrically, I could start with either the 10 grams of ethane and then do this whole process here, but with the other reactant, going from ethane to oxygen in a 2 to 7 ratio. Or you could pick one of the masses of the products. There's often many ways to do a stoichiometry problem, and it's often going to get you to the same answer because of the internal logic of the chemical equation. So here, in this case, I used the 18 grams of water. I divided by the molar mass of water. That should be 18.02. Whoops. I don't think it affects the math, though. And then that's going to be a 7 to 6 ratio from water to oxygen. So I have 7 moles of O2 over 6 moles of H2O, and then I multiply by the molar mass of oxygen, and I end up with 37.3 grams of O2 total, which is the exact same number that I got using my conservation of mass assumption. So that tells us that our assumption was correct, but also that you can get to the same answer using the stoichiometric math. All right, so I've kind of summarized this idea before, but I wanted to summarize this before we start getting into limiting reactant problems. If you ever have one reactant with a specific amount, we could just use the normal method that I've been doing here, where you just go from mass or volume to moles and then to mass or volume. If there are 2 reactants, and you're given a specific amount of one in excess of the other, this is kind of like a limiting reactant problem that already tells you which one is limiting. The one that is not excess is the one that's going to control how much product you can make. So you can just basically do the same process and ignore the excess one unless it asks you to do something with it like the last one did. However, If there are two reactants and you're given specific amounts of both of them, that is definitely a limiting reactant problem, and you're going to have to do some extra steps in order to determine which of the two reactants is going to be limiting and which one is going to control how much product you can make. So let's look at an example of that. So in this case, we have ammonia reacting with oxygen to make nitrogen monoxide and water. We're given that we have 3.25 grams of ammonia and 3.5 grams of oxygen. So this is what I was talking about. I have specific amounts of both of the reactants. So in order to figure out anything about the products, I'm going to need to figure out which substances is limiting, how many moles of each that we need to make the reaction go, and which substance is going to run out first, because that's the one that's going to control how much product can be made. You'll also notice that this chemical equation is not balanced. So what I would like y'all to do is pause the video real quick and try to balance this equation on your own, because I'm going to show you the answer in the next slide. All right, so the balanced equation has a 4 to 5 to 4 to 6 ratio, and that's going to be important to make sure we do this right. So let's start by converting our grams of both reactants into moles, because that's going to be important to figure out who the limiting reactant is. So for the ammonia, I divide by the molar mass, I get 0.191 moles of ammonia. For the oxygen, I divide by the molar mass, I get 0.11. It's technically 0.109. I should do more sig figs here just in case. Okay, so now let's consider the ratio of the substances. So one way to figure out who the limiting reactant is to calculate how many moles of the other reactant you would need to react with all of the moles of reactant that you have. So what I mean by that is here I'm starting with 0.191 moles of ammonia, and I want to figure out how many moles of oxygen I need. So how much oxygen I need to react with all of the ammonia that I have. So I take my moles of ammonia, I multiply it by the mole ratio, which in this case is 5/4 moles. That gives me 0.240 moles of O2 needed to react with all of the ammonia. And you'll notice something, that we only have 0.109 moles of O2. So that already tells us something, but let's go through all of the logic here. If I have my 0.109 moles of O2, and I do the same thing, I calculate how much ammonia I need to react with all of it, that's going to be a 4/5 ratio. That gives me 0.087 moles of ammonia needed. And you'll notice that if I compare what I need to what I have, that will sort of identify who is limiting. Because in order to react all of the ammonia, I would need 0.24 moles of O2 when I only have 0.109. So I don't have enough oxygen to react with all of the ammonia. So that tells us that the oxygen is limited. And this is further proven by the point that if I have 0.109 moles of O2 and I want to react all of it, I'm going to need 0.087 moles of ammonia. If I compare that to what I have 0.191. I have more than twice that. So I have an excess of ammonia, and oxygen is going to be our limiting reactant, which means that if I want to calculate anything about the products, I'm going to either have to use the given amount of oxygen or the calculated amount of ammonia that is actually needed. Because even though we have 0.191 moles of ammonia, only 0.087 of it are going to react. And once the oxygen is used up, the reaction is going to stop. So let's look at how to do something with this. Oh, this is just me summarizing the same thing that I just did. All right, let's do a problem where we want to figure out how many grams of nitrogen monoxide are formed at the end of the reaction. So I want to calculate how much of this is formed based off of the amounts that I was given earlier. I also want to figure out how many grams of excess reactant we have left. So we had specific amounts of both reactants. One of them is going to completely run out, and another one is going to have a certain amount of mass left over. So let's calculate it. So the moles of limiting reactant we can use to find the moles of product. So that was my 0.109 moles of O2. I'm trying to figure out the grams of NO. So that's going to be a 4/5 ratio. And then I can multiply by the molar mass of NO, and that gives me 2.6 grams of NO. That's going to be my final answer here. You can see I have 2 sig figs. That's because in the original problem, I had 3 for ammonia and 2 for oxygen. So I'm going to be limited by that 2 there. And now if I want to figure out how many grams of excess reactant we have left, I'm going to start with the 0.191 moles of ammonia, except we only used 0.087 of it. That's when we calculated how much of the ammonia we would need to react with all of the oxygen. That's going to tell us how much of the ammonia actually reacts. So the difference between how much I started with and how much I actually used is going to tell us how much is left over. So if I do 0.191 minus 0.087, there's going to be 0.104 moles of the ammonia left over. And then I can just take that and convert it into mass using the molar mass, which is going to give us 1.8 grams of ammonia left over. So we actually had a lot, like I said, over since there was more than double what we needed, we're going to have more than half left. However, this is not the only way to do this problem. Say we didn't need to know anything about the excess reactant. We just wanted to know how many grams of the NO were formed. Another way we could do this would be to start with our 3.25 grams and then just do all of the math to calculate how much NO we would form, and then do the same thing for the 3.5 grams of oxygen. In either case, we're ignoring the other reactant, because then if you look at how many grams of NO are formed in both cases, the one that forms less is going to be the true one, because if that's the maximum amount of NO that you can form based off of the amount of reactant given, there's no way the bigger one could be true. So if you were to do this, you'd probably end up with some bigger value and then also 2.6, and then you can identify that the 2.6 was the lesser one, which identifies that the oxygen is the limiting reactant. However, this doesn't work if we wanted to figure out how many grams of excess reactant we had left, because we needed to do that equation here to calculate how much of the ammonia was actually needed. So that is all I have to say today for stoichiometry and chemical equations, and I'll see you in the next part of the Unit 4. All right, bye.